All right, let's take a minute and look and see exactly what a chi-square test looks like and what your null and alternative hypothesis would look like. The chi-square test statistic will tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much from the one claimed by the company as the bag does. So basically what we're doing with our chi-square goodness of fit is we're just checking to see how far away are the observed counts from the expected counts. If they're not very far away, then that means we got what the company suspected we should get. If they are far away, then that means that what we got is not what we expected, and the distributions would look different. So what will your null and alternative hypothesis look like for this situation? The null hypothesis in a chi-square goodness of fit test is always claiming that the distributions are equal. So this null specifically would look like the company's stated color distribution for M&Ms is correct, or the distribution of the colored M&Ms that is predicted is the same as what we get. So we're basically just saying that the two distributions are the same, or that what the company is claiming is correct. That's the same thing as saying that they are the same. Okay, now the alternative hypothesis is always going to look the same. The alternative hypothesis in a chi-square goodness of fit test is saying that the categorical variable does not have the distribution that is stated by the company, or that the distributions are not equal. Okay, so it's not a fancy alternative. It's always going to be the same. The company's stated color distribution for M&Ms is not correct. So you're saying something about it's not the same, it's not correct, one of the distributions is different. And remember, when we're doing this, we don't know, it might not be that all of the colors are off. Even if one color is off from the observed, okay, even if one color is different than what it should be, then the distributions are different. But we're not testing each one individually, we're testing them overall. Okay, now you could also write it like this. This takes a little bit longer to write. So you're saying you're writing out all of the probabilities or the proportions of each of the different colors. Okay, so that is like saying that the what the company stated is correct, and the alternative is just saying at least one of them is incorrect. Okay, and here you'd have to define what P of color means. It's the true population proportion of M&Ms, of candies of that color. So this just takes a little bit longer, so I suggest just writing that the distributions are the same, or what is expected. Make sure you're also writing that in context. Okay, the idea of a chi-square goodness of fit is this, what we've been talking about, that we're comparing the observed counts from our sample with the counts from the expected value. So are they the same or are they different? Now, here's something key. The more that the observed counts differ from the expected counts, the more evidence we have against the null, which makes sense because if they're far away from the expected, then that's stronger evidence to show us that what we got is not what we should have gotten. Okay, all right, so to see if the data gives convincing evidence against the null, we compare the observed counts with our sample from the expected accounts, assuming the null is true. Oh, notice there's our p-value. So we're assuming that the company is correct. We're assuming that the distributions are the same, and we're checking to see what did our data say? Did our data say that the observed and the expected are the same, or they're different? If the observed counts are far from the expected counts, then that's the evidence that we're looking for against the null. So take a look here. So take a look at these distributions. Blue, okay, this is my observed, and this is what we expected to get. There's a pretty big difference here. Orange, this is what we observed, this is what we expected to get. This one's not quite as bad. Look at the yellow. This is what we observed, and this is what we expected, and these two are not that much off. There's some fairly large differences between the observed and the expected. How likely is it that the difference is large enough that occurred by chance alone, or, okay, just by chance, I just so happened in this bag that my colors are different, or is what the company is saying is not incorrect. Now, later on, we're going to look at a follow-up analysis, and I just kind of want you to see what that means. Is your follow-up analysis is going to say, which chi-square statistic, so which of these differences is going to contribute the most? Well, just by looking at this, look at the yellow. The yellow is one of the furthest off, so that's going to contribute to my chi-square statistic. That's going to say, okay, that is much different. Also the blue. Okay, see the large difference between the observed and the expected. So just kind of have that in the back of your mind when we go through that. Now, to answer this question, we are going to calculate the chi-square statistic. The chi-square statistic basically just says how far is the observed value from the expected value. Now, here's how you get the chi-square statistic. I will never make you do this by hand. You can always get this from your graphing calculator. It's very easy to get, so just make sure you understand where it's coming from. Now, your formula for your chi-square statistic is you're taking your observed value, and this is for each individual one. You're taking your observed value, subtracting the expected value, that's why we have to calculate the expected value, squaring that answer and dividing it by the expected. So O minus E over E. Okay, so notice what this sigma means. That means you're doing this for each of them. So we take the blue, observed minus expected, square divided by expected. Then remember that sigma means I'm adding them together. Okay, so then I would be adding, so we'd find it for the blue, and then we'd find it for the orange, and then we'd find it for the yellow, and we would add all of those together. Okay, so observed minus expected squared all over the expected. Add each of those together, and that is going to give you your chi-square statistic. Okay, now please keep in mind here, when you're doing this, you're using the counts, not the proportion. So when I say observed minus expected, it's the counts that we observed minus the expected counts squared divided by your expected counts. Now, like I said, you're going to get this all from your graphing calculator. Okay, you will have to show 2 steps for this. So 2 of these, you'll have to write out what they are. Then you'll just get the answer from your calculator. It's very easy to get. Okay, so let's see what this chi-square statistic looks like if we were going to calculate it by hand. So remember, this is our count. So here's ours observed. Here's our expected. Okay, so what we did here, where did this first one come from? Take a look at this. We have, okay, 9 minus 14.4 squared divided by 14.4. 8 minus 12 squared divided by 12. 12 minus 9.6 squared divided by 9.6. So that chi-squared statistic is every single one of these. Okay, see how far away the observed is from the expected. And then what we just did is we added them all up to get my chi-square statistic. So I just wanted you to take a look at this quickly and see if we notice which ones are the furthest. Look at this one right here. This is a pretty large value, so that's saying that it's pretty far away, you know, from the observed value. And here's my second one. Okay, and that came from the blue. And this one came from the yellow. Okay, so remember we said that the blue and the yellow were the furthest away. So there are largest numbers, if you notice, that are contributing to our final answer of our chi-square statistic as 10.180. Now, think about this. What does a large chi-square statistic mean versus a small chi-square statistic? If we get a small chi-squared statistic, okay, so if you get chi-squared, you know, is equal to 1, or it's equal to even 2, or it's equal to 0.5, okay? If the chi-square statistic is 0, then the observed counts are the same as the expected counts. Well, why? Because you're doing the observed minus the expected squared all over your expected. If they're the same, these two are the same, then you're going to end up getting 0, okay, over your expected, which is just 0. All right, so that means if I have small chi-square statistic, when I did this subtraction, it wasn't very large, so there was not a large difference. However, if when I did this subtraction and I got a large number for my chi-square statistic, that's saying they are really far off from each other. Now, what we're going to do next is take a look at the chi-square distribution and see how we get the p-value. Okay, so here's how we're going to get the chi-square statistic. You can do this by hand, but it's going to take a lot of time, and I said you don't need to do that. Let's take a look and see how you're going to do this on your graphing calculator. So the first thing you're going to do is you're going to go to list 1, and you're going to type in your observed counts, okay? Then you're going to go to list 2, and you're going to calculate your expected counts. Now, if your expected counts are not given, you can literally just take n, which is your total in this case, which was 60, times the probability that it occurred. The first one was 0.24. Type that into list 2, and then that will just automatically populate as 14.4. Okay? Now, and then what you're going to do is highlight list 3, and you're basically using your list 1 and your list 2 to get that information. So you're taking list 1, okay, putting that in parentheses and subtracting list 2. Notice how list 3 is highlighted as you're doing this, okay? Squaring it, and then divide by list 2, because list 1 is our observed, list 2 is our expected. Make sure you put that in parentheses and square it, all divided by my list 2, okay? All right, so then, now you have list 3. So now what we're going to do is we're going to sum list 3 to get my chi-square statistic. So you're going to go to second, hit list, go to math, go over to sum, okay, go down to sum right here, and then make sure you hit enter. It'll take you to your home screen, and you're going to hit L3, and that will give you your chi-square statistic. So that's a way to do it by hand. However, your graphing calculator, when you do the chi-square test, will give it to you with almost no work required. So we'll be going over that later. All right, so let's take a look at the sampling distribution of the chi-square statistic. It's actually not a normal distribution. It's right skewed, which means that we're only going to have positive values. Because notice when we did our observed minus our expected, we squared them, and that made all of my values positive. So how are we going to be able to tell if the sampling distribution that we're looking at is a chi-square distribution? It will never look normal. It is always going to be right skewed like this. So what you're going to have to do, one of your conditions, you're not going to have a normal condition here. You're going to have a chi-squared sort of condition. And what you're going to do is you're going to check to see that all the expected counts are at least 5. Then we know we have a chi-squared distribution. So it is important that in all of your chi-square tests, you show those expected values to show that, in fact, all of your expected counts are greater than 5, okay? Now, there are a family of distributions that only take on positive values, and they're always skewed to the right. So it's specified by the degrees of freedom, just like our test statistic T. The chi-square goodness of fit test uses the chi-square distribution with degrees of freedom, which is the number of categories minus 1. So be careful with that. Take a look at your degrees of freedom. So degrees of freedom in 8 actually looks kind of normal, even though you don't have any negative values. Take a look at degrees of freedom in 4, very right skewed, 1, super right skewed. So you always have to state your degrees of freedom just like your T distribution. All right, so let's take a look at a quick summary. The distribution of chi-square statistic is positive, okay? When I say 1 parameter degrees of freedom, you take your categories minus 1. The characteristics are, same thing with a normal curve, total area is 1, n minus 1 degrees of freedom, where n is your categories, not the sample size here. Be careful with that. It is not your sample size. Count the categories in your table, okay? It's n minus 1 because all the variables can vary, but the last one has to ensure that it adds up to 100% of the area under the curve. The curve begins at 0 on the horizontal axis and is skewed right. As the degrees of freedom increases, it looks a little bit more normal, just like we talked about.